Time for a pop quiz. Hardly even a practice test.
Hi, Martin. Welcome in. How are you doing? Second try is always a charm, right? Thank you very much for the wishes on the affiliate anniversary. Yeah. It's been about 2 years actually, I think. About 2 years. That's crazy. Maybe 3 actually. It's time flies when you're streaming on Twitch, let me tell you. All right, so we're about 1 minute out from starting the real analysis group. I'm just trying to get my monitoring device on here. Here we go. Time flies when you're struggling with math. True. You should have seen me struggling with physics. Holy moly. Time did not fly while I was struggling for physics. That's for a fact. Okay, we're almost ready here. What the heck? Man, this computer is dying. Tidying up some notes from topology. Sweet. I need to relook at topology again. And I think they're going to be starting a topology reading group in Simple Server as well. Probably following Munkers by the sounds of it. So it'll be nice to revisit some of those ideas and kind of generalize what we're doing in this particular reading group too. No, topology is definitely not my favorite topic either. Actually, I might take that 30 seconds to go grab a little top up of coffee.
Oh yeah? Prepare to be iterated.
I might leave her on 1. All right, everybody, we are back. Let me do a couple things here. So, ba-boom, hello, my name is Penn Center. We are live on Twitch with the reading group in Real Analysis. This is the second part, and we have an awesome presentation. I've been looking over the slide deck, and it's fantastic. So, we're going to pop over into the Mathematics, the Mandelbrot Discord server, and we're going to let Dingus do their thing. They're going to be talking a little bit about the Axiom of Completeness, as well as sequential limits and some of the properties that go along with that. So without further ado, I'm going to pop on over. All right, so hello everyone, and welcome on in. My name is Penn Center. Welcome into the second part of the Real Analysis reading group. I've had a chance to take a look at the slide deck. I'm super excited can I refer to you as Dingus? Is that okay?
Yes. Yes.
Okay. Because I also noticed that your handle is Sir Dingus, so I was also wondering if you had been knighted or not.
No, that was just a silly. Dingus was taken, so I just went with Sir Dingus.
Yeah. Cool.
Yeah.
So Dingus is going to be here chatting a little bit about the Axiom of Completeness, as well as some of the kind of introductory topics in sequential limits. So without further ado, so what I usually do, Dingus, is I'll just kind of be on, I'll be on mute, both on Twitch and on Discord, and just kind of monitoring the chats. And if there's anything kind of specific with regards to questions that I think might be good to answer, I might just kind of pause you at a good time and ask that question, if that's okay with you.
Okay, sounds good.
Awesome. All right, so the stage is all yours.
Thank you. So thank you guys all for coming. I'm really excited about this. I really enjoy these beginning real analysis topics because we're going to be talking about some very common theorems and ideas that you guys will be using throughout this entire, reading group and throughout your entire study of real analysis. So as far as what we're going to cover today, we are going to do a brief introduction to real numbers because that's what real analysis is. It's the study of real numbers. And then we're going to go over a bunch of theorems that will be useful later on. And then we will be getting to our limits of sequences and some of the properties of limits that you may be familiar from calculus. So we're going to be starting with our reals and initial theorems. So I based most of this on the textbook by Abbott that I believe is linked somewhere in the Discord. And in chapter 1, Abbott gives a very vague description of the real numbers and promises that later on in the course, or the book or whatever, he'll explain a more rigorous definition of the real numbers. So we're going to use this kind of vague idea for now, and it'll be enough for what we need right now. So pretty much introduction to real numbers. The real numbers are denoted by this boldface R if you have not seen it before. So if you see this later on, that's what I'm referring to. And a large part of the real numbers is that it contains the rational numbers. And for those of you who may not know what the rational numbers are, they're pretty much any numbers of the form m over n, where m is an element of the integers, which is that boldface C, and n is an element of the natural numbers. So it's pretty much, any fractions, any integers, anything like that. And then we are also told in Abbott that R is an ordered field. That does not really come up too much. Pretty much all that means is it has all four operations, addition, subtraction, multiplication, division, and we can pretty much use them how we're used to using them. And then so if a big part of the real numbers is that they contain the rational numbers, what makes real numbers different than the rationals? And essentially, the real numbers have this property called the Axiom of Completeness. And we are going to go over this pretty soon, but in common terms, it just pretty much means there's no gaps in the real number line. Because with the rational numbers, right? You may have a rational number here and a rational number here, but there could be, irrationals or something in between. So there could be little gaps. And the axiom of completeness essentially says that we don't have any of those gaps. So before we get into the axiom of completeness, I'm just going to go over a few definitions that will be helpful. So we say a set A that's a subset of the real numbers. It is bounded above if there exists a number B in R such that A is less than or equal to B for all A and A. And that's just a fancy way of saying if we have an interval and we have some number B and we know that all the terms of some set A are over here, whatever, they're less than or equal to B, then then the set is bounded above. So an important note is that upper bounds are not unique. For example, let A equal this set of 1, 2, 3, 4. There's an infinite amount of upper bounds, but some of them include 4, 97, and this very large number. There's a lot of them. But similarly, the set A is bounded below if there exists a lower bound L in R, satisfying L is less than or equal to A for every A element of A. So again, that's just pretty much saying if we have a number down here, like an L, and we know there's nothing less than that, we have lower bound. Okay. And then as with upper bounds, lower bounds are not unique. So if we have A, pretty much A is just any real number in the interval 0, 1. We have some lower bounds of A include 0, -pi, and -5082. Again, there are infinite amounts of lower bounds. Those are just a few examples. So more definitions is that we have a real number S is the least upper bound for a set A element, or A and R, if it meets the following two criteria. So one, it has to be an upper bound for A. That's important to be the least upper bound. And then if you have any upper bound for A, then S has to be less than or equal to B. And all that's saying is if you have your real number line, you know that S is an upper bound. Any other S or any other upper bound has to be up here somewhere. We can't have an upper bound like right here because S is the least upper bound. And then a real number M is the, okay, that should not say least upper bound. That should say greatest lower bound. A real number M is the greatest lower bound for a set A and R if it meets the following two criteria. Again, it has to be a lower bound, and it has to be greater than all the other lower bounds. So it's essentially the same thing, just you have a lower bound, and any other lower bound is going to be less than that. So in the case of the greatest upper bound or the least upper bound, we have that number called the supremum of A. We denoted sup A. And then M, which is the greatest lower bound, is called the infimum of A. And so yeah, we'll be using those terms quite a lot. So unlike upper and lower bounds, supremums and infimums are unique. They may or may not be contained in the set. One thing to think about is if a set has a maximum or minimum, that element is going to be the supremum or infimum. So that's a little thing to think about maybe if you're interested. And then for some examples, I just took the same sets that we did using the last slide. We have A equals the set of 1, 2, 3, and 4, or at least upper bound is going to be 4, and our greatest lower bound is going to be 1. And we're going to pretty soon go into how to rigorously prove that certain numbers are supremums or infimums. And then back to our B set, which is pretty much anything in the interval 0, 1. Our supremum of A is going to be 1, and our infimum of A is going to be 0. And notice in set A, both our supremum and infimum were included in the set. In B, neither of them were included in the set. So it doesn't matter if they're included in the set or not. They just have to follow the criteria. And another thing to note is it's not always true that if the supremum's in the set, the infimum is also in the set. Sometimes you can have a set that contains its infimum and not a supremum, or vice versa. So then the question becomes, can we ever guarantee the existence of a supremum or an infimum? And the answer is yes. We have the axiom of completeness, which I copied from Abbott, and it says every non-empty set of real numbers that is bounded above has a least upper bound. So essentially, if you have an upper bound, there's one that's less than all the other upper bounds. It seems kind of intuitive, but we're going to be using this a good amount. So some consequences of the axiom of completeness is that the axiom does not state what the supremum of the set is. It can guarantee you that we do have a supremum or infimum, but it will not tell you what that number is. That's up to us to figure out. And supremums and infimums are unique. I added a little preview because notice the axiom of completeness only talks about upper bounds and supremums. So something to think about. What does it say about infimums, if anything? And we're going to go over that a bit later. So another consequence is that the axiom of completeness, like I said before, is kind of what separates the real numbers from the rational numbers. So for example, it doesn't work for the rational numbers because if we consider the set A is A where x is a rational number but its square is less than 2, then this does have a supremum in the real numbers, but not in the rational numbers. Because obviously, with our knowledge of square roots, which we haven't defined yet, we'd know that square root of 2 would be the supremum. But obviously that is not a rational number. So essentially, we just don't have a supremum in the rational numbers. And then we are going to go over a proof of a supremum and an infimum. So this is just example 1.3.7 from Abbott. So we have that A in R is a non-empty and bounded above set. And then we're going to let a real number C be an element of R. So we're going to have the set C plus A be, that should be an uppercase A. C plus A equals, all the terms, you just add C to every term in A. And then we're going to prove that supremum of C plus A equals C plus the supremum of A. Which should be kind of intuitive, but unfortunately intuition doesn't get us very far in analysis. We actually have to rigorously prove what we're claiming. So I broke this into a few steps. Step 0, we need to prove that the supremum and infimum exists. Now this is not always necessary. You'll notice in Abbott, for example, they pretty quickly stop proving that the supremum or infimum exists. They just assume that you can tell that the axiom of completeness and you can tell whether or not it exists. But I think it's a very good idea to verify that it exists, just so you're not proving something that doesn't exist, because that would cause problems. So essentially, we are given in the problem that A in R is non-empty and bounded above. Those are the exact conditions we need to use the axiom of completeness. So we know supremum of A exists. Note that for all choices of C and A, both of them in the real numbers, C plus A is also going to be in the real numbers by closure under addition of the real numbers. And again, that comes from the fact that real numbers are an ordered field. But again, we don't really need to know that. It's just by closure. Oh, and if you guys do not know what closure means, that pretty much means that if we have two elements of the real numbers and we add them together, then that result is also going to be in the real numbers, and that's closure under addition. So anyways, we have that C plus A plus the set A is going to be a subset of R because all of the elements in that set will be in R. So since A is non-empty, we know that there exists an element in A. Consequently, there is an element C plus A, and we know that C plus big A is non-empty. And then on the next slide, we are going to prove that C plus A is bounded above. And so this is where step 1 comes in. We do need to prove that the desired supremum or infimum is an upper or lower bound. That is important. So to do this, we're going to let S, we're going to just denote supremum of A as S because it's less cumbersome to write S every time. So by the definition of a supremum, we know that S is greater than or equal to A for all A in A. And so we can just add C to both sides of the inequality, and we get that C plus S is greater than equal to C plus A for all A in A. So that's exactly what we wanted. We just found an upper bound for C plus A. And then I put a little side note that step 1 is complete because we proved that there's an upper bound. But I just also wanted to point out that now that we've determined it's bounded above, notice we didn't do that on this slide. We only did it here. This is the last condition that we needed to conclude from step 0 that the supremum does exist. And then step 2, prove desired supremum or infimum is the least or greatest bound. So now we're going to prove that the supremum is the least upper bound. To do so, we're going to take another number B, and we're just going to say it's some upper bound of C plus A. So by definition, C plus A is going to be less than or equal to B for all A and A. That's just from the definition of an upper bound. And then if we rearrange the inequality by subtracting C from both sides, we get A is less than or equal to B minus C. So again, by the definition of upper bounds, we know that B minus C is an upper bound for A. We know that S is the least upper bound of A, and people may be saying that's circular reasoning, but notice that we're talking about the upper bound of A, not the upper bound of C plus A, which is what we're trying to prove. So we can say for sure that S is the least upper bound of A. And then we can write that S is less than or equal to B minus C. That just comes from the fact that it's the least upper bound. And then if you add C to both sides of the inequality, you get S plus C is less than or equal to B. And since B is an arbitrary upper bound, and we found a number that's less than or equal to it, and we know that S plus C is an upper bound, and essentially that means that we've just proven that S plus C is the least upper bound of C plus A. We went through the steps, we got that it is an upper bound, and if there's any other upper bound, it's less than or equal to the upper bound. So those are kind of the general steps that we have to take for these supremum and infimum proofs. And yeah. So now we have a lemma 1.3.8. And this essentially is another definition for supremum. So if we have S in R is an upper bound for a set A subset of R, then S equals supremum of A if and only if, for every choice of epsilon greater than 0, there exists an element A in A satisfying S minus epsilon less than A. So if you have not seen these kind of epsilon statements and proofs yet, you might want to get used to them because we will be using them a lot. Essentially, epsilon is often taken to be, it's by convention, is intended to be a very, very small number. It doesn't have to be, but kind of when you see an epsilon, that generally indicates that somebody is trying to get something very, very small. And essentially, all this is saying is if we have our number line and we have our supremum S and our elements A, we're saying that if S is truly the supremum of A, if we take a very small number and subtract it from S, then we can find another A in that area. Yeah, and so that's essentially what that's doing for us is we're saying we can't find a lower upper bound because if we could, then we could say, oh, S minus epsilon is a lower bound because there's no A over here. So essentially what this does is this says, okay, if we try to subtract anything from our supremum, we're going to have another a in there. We can't find another lower upper bound. And then a little side note, I noticed that proof by contradiction was not covered last week, so I just thought I'd do a little introduction. Essentially, the steps for proof by contradiction are you assume a contradiction. So you negate the statement that you want to prove. You say, okay, say this statement's true. We know it's false, but we're going to say it's true. Then we do math. Very descriptive, I know. You pretty much just follow a train of logical conclusions, like what do you know, what can you imply, what can you use to advance just an argument. And then eventually you should find a problem. You should reach a contradiction, and that will tell you that the original statement is indeed false. And I introduced this because we will be using contradiction in this next proof. So going back to the preview that I mentioned earlier, what does the Axiom of Completeness, that's what this AOC stands for. Axiom of Completeness. So what does it imply about infimums? So pretty much the answer is it implies that if a non-empty subset of the real numbers is bounded below, then the infimum of the set exists. It doesn't directly state that, but we're going to prove this, actually. And it just follows from the axiom of completeness. So we're going to prove the following. Let A be non-empty and bounded below, and define B in R where B is a lower bound for A. Show that supremum B equals infimum A. So essentially our strategy here is we're going to say that we have a set A and we have a lower bound for A. We know it's bounded below. And so we're going to take B to be the set all the way over here of all the lower bounds of A. And we are going to show that this upper bound of the lower bounds is the infimum of A. So essentially, I did a brief note that the axiom of completeness implies that supremum of B exists because B is a lower bound. We know it can't keep going forever because then eventually we'll get into A. So we know that the upper bound of B exists, and so we know that supremum of B exists. So now we just need to prove that the supremum of B also meets the criteria to be defined as infimum of A. So first step in proving any supremum or infimum is that we need to prove that the infimum, our proposed infimum, is actually a lower bound of A. So we are going to start by contradiction, and we're going to assume for contradiction that K is not a lower bound of A. Remember, K is how we define supremum of B. So we're saying this obviously false statement, and then we're going to try to find a problem from it. So we assume that it's not a lower bound of A. Consequently, there exists an A in the big set, in the set A, such that A is less than K. So we're saying K is not lower bound of A, we've got a term below it. And I'm just going to rearrange that and say that K minus A is greater than 0. So by lemma 1.3.8, which is what we just talked about, this guy, for every choice of epsilon greater than 0, there exists an element B in B satisfying K minus epsilon is less than B. So that just follows straight from the lemma. And we proved above that epsilon equals K minus A is valid because K minus A is greater than 0. And we know that for this theorem that for every choice of epsilon greater than 0, So we can say epsilon equals k minus a. That's a valid choice of epsilon. So if we substitute k minus a for epsilon in this inequality we had over here, we get k minus a is less than b. And that simplifies to a is less than b. Now that is a contradiction. We found our problem because we defined b to be less than or equal to a for all b and a. So now we assumed that k was not lower bound of a. We found a contradiction. So now we can conclude that it is a lower bound of a. Okay, and then the next step is to prove the desired supremum or infimum is the least or the greatest bound. We're talking about infimums here, so we're going to prove that it's the greatest bound. This is much simpler than the previous step because it directly follows from the definition that k is the supremum of b. We literally know that it's greater than or equal to all other b's. And we finished the two steps. We proved that k was a lower bound of a, and also that it's the greatest lower bound. So we can conclude that the supremum of b is the infimum of a. And if you guys have not seen this little QED over here, that is just a symbol that means we are done with the proof. Yeah. And so how does this relate to the axiom of completeness? So all that the axiom of completeness directly guarantees is that we have a supremum for sets that are bounded above. However, we just showed that for any set that's bounded below, we can construct a set of lower bounds whose supremum is the infimum of a. So we can guarantee the infimum of a if it's bounded below. So that was kind of one big theorem. We're going to now introduce a few more major theorems that are going to be very useful in continuing analysis. So we're going to start with the nested interval property. And for each n in the natural numbers, assume we're given a closed interval. And this is just a fancy way of saying we have an interval like this. This is like the more rigorous definition. But we just have our typical interval. So like 1, 2, or 3, 4, for example. And then we're going to assume also that each I sub n also contains I sub n plus 1. And all that means is if we have our A sub 1, B sub 1 for I1, then our I2, its bounds are going to be somewhere within that. And similarly for I3, we'll have A3 is in there and B3 there, so it's completely contained in the previous interval. And then, so we have the resulting nested sequence of closed intervals where I1 contains I2, which contains I3, which contains I4, which goes on forever. And we are going to prove that that has a non-empty intersection. That means that if we take the intersection of all of them, or if we find what's common to all of the sets, then it's not going to equal the empty set. We're going to actually have an element in there. And I will point out really fast that it does have to be a closed interval. You can find easily that if you have an open interval, this does not necessarily hold. So we're going to do the proof right now. So we haven't talked about many strategies that we have, but we do have the axiom of completeness, which we love and appreciate. And so we are going to use that. And so we're going to use it to find an x in the real numbers such that x is in every single interval. That's pretty much the definition of an intersection not being empty in this case. So we're going to, essentially what we're doing is we're realizing that, like above, or I can just use the picture above, right? We have A1's on the left, our A's on the left, B's on the right. And due to this nested interval property, we can kind of consider all of the A's one sequence and all of the B's another, because we know that in order for it to keep being nested, these B's are always going to have to be greater than these A's. So that's essentially what I said here. I just said that we know that each B sub n, the right endpoint of each closed interval, that's going to be greater than or equal to all of the A sub n's. Consequently, we know that A is bounded above. So we know by the axiom of completeness that supremum of A, which we're going to call X, exists. So now we're just going to consider an arbitrary I sub n, one of those intervals that's nested in all the other ones before it, and all the intervals afterwards are nested in that. By definition, we know that X is greater than or equal to A sub n because we defined the supremum of A as X. So we know that B sub n is an upper bound of A, and X is the least upper bound of A. X is going to be less than or equal to B sub n for all the B sub n's. So now we have an inequality that A sub n is less than or equal to X, which is less than or equal to B sub n. Because we just chose this I sub n to be arbitrary and we didn't set a fixed value to it, we can generalize this to say that for all n and n in the natural numbers, we are guaranteed to have an X in that interval, and consequently, the intersection is going to be non-empty, which is very nice. And then, my favorite property, the Archimedean property. So there are a few different versions of the Archimedean property. I took this one from Zacon, I don't know how you say it. But this is kind of the general, most common version of the Archimedean property that you'll see. And essentially it just says if you have any x greater than 0 and any y, you can find a natural number in n such that nx is greater than y. And essentially that's pretty much just saying in simple terms that the natural numbers are unbounded above. We can always find a natural number greater than other natural numbers. So I also included the Abbott version because I think it is a little more clear than this general version about exactly how we can apply this. So it breaks it into two pieces. It's saying if we have any number x and r, we can find a natural number that is greater than that number. So pretty much this unbounded thing. And then also it says that if we have any real number, y is greater than 0, we can find an n satisfying 1 over n is less than y. So that's just saying if we have like some interval and we have 0 over here and we just have some y, it can be as small as we want, as big as we want. We can always find a 1 over n in there. And this Archimedean property is essential. We're going to be using it all the time in all sorts of proofs, whether or not we explicitly state it. So it is a very nice property to have. And essentially, I just introduced two different versions of the Archimedean property. So I just wanted to do a quick side note. We're not going to prove it, but we're going to sketch or propose why it's equivalent, why the two are equivalent. So we have the Zacon, whatever, to Abbott proof. So if we take Zacon's version and we say that, and we let x equal 1, notice that we get n is greater than y. So that's exactly what we said. They just switched x and y here. So just by letting x be 1, we get n is greater than y. So that implies part 1. And then if we let y equal 1, then we're going to get nx equals 1. X is greater than 1 over n, which is exactly what part 2 is saying. We're saying we can find a 1 over n less than y, again, they switched x and y, but it means the same thing. So we know that this version, the first version, implies the second version.
QED.
Now, to go from Abbott to the first one is a little bit more work, but it's still not too bad. So we notice that if x and y are in R and x is greater than 0, then we have y over x is element
Nicely
of R.
integrated.
This follows again from the fact that R is an ordered field, and we know that division is closed, that the real numbers are closed under division.
Nicely integrated.
So we have that y over x
Problem
is in R,
solved.
and we know that part 1, which was this part, means that there exists an n in n such that y over x is less than n. So again, we're saying we can find a natural number bigger than it. This implies that y is less than nx, which is exactly what the first version says. So these definitions are equivalent. I prefer Abbott just because it kind of breaks it down into 2 cases and just really tells us how we can use them in proofs, but you can use either version and they're equivalent, so it doesn't really matter. So I wanted to do a proof of the Archimedean property, which I'm going to call AP because that's a long name, Archimedean property, and takes up a lot of space. So essentially, we're going to first prove the first part. The first part was saying that if we have any real number, we can find a natural number bigger than it. So again, we're going to use contradiction again, and we're going to assume for a contradiction that n is less than or equal to x for all n in the natural numbers. So essentially, we're saying that the natural numbers are bounded above. And we can just say that 1's a natural number, so it's non-empty. So we have x is an upper bound of n. The axiom of completeness guarantees that the supremum of the natural numbers exists. Now, some of you who have done a lot of this before might be freaking out that I just wrote that the supremum of the natural numbers exists when it clearly does not. Remember, this is a contradiction, so we are assuming something that is completely false. And so we're going to set alpha to equal supremum of n. And then by the lemma 1.3.8, that was the one that involved the epsilons. We know there exists an n in n such that alpha minus 1 is less than n. And essentially here I just put that 1 equals our epsilon. Again, I just chose an epsilon because if it holds for all epsilons, it should hold in particular for this epsilon. So if we add 1 to both sides, we get alpha is less than n plus 1. However, under addition of the natural numbers, we are guaranteed that n plus 1 is a natural number. So now we have a contradiction because we said alpha was an upper bound of the natural numbers. So we can now conclude that because we assumed a false statement and it caused the problem, we can assume that the statement we originally wanted to prove is true. So we can say x or n is not bounded from above, and given any real number, we can find an n greater than that. Now, the proof of the second part, which is talking about finding numbers smaller than other real numbers, we just use closure under division again, and we say 1 over y is a real number, because y is a real number. And then we know from part 1 that we can find an n such that n is greater than 1 over y. And then if you multiply both sides by y, remember we defined y to be greater than 0, so we don't have any problems. We get that ny is greater than 1, which if we divide both sides by n, we get 1 over n is less than y, which is exactly what we were trying to prove. So that's the general idea behind the Archimedean property, and we will be using it a lot, like I said. So now I'm going to introduce another little concept, or I won't call it little, but another cool concept, which is density. And essentially, density in a set means that if we have a set A dense and a set B, for every choice, so that means if, okay, so let me start over. So we have a set A is dense in a set B if for every choice of B and C and B, so we're taking two elements of B, where B is less than C, then we can find an A in A such that A is between them. So we often talk about density in R. We say the rationals is dense in R. So essentially what that's saying is if we find any two real numbers, A and B, they don't have to be rational, they just have to be real. We can find an element of Q, I'll just call it Q for now, in between those two. And we're going to prove that in a second. But going through some other sets, we have this set of irrational numbers is dense in R. Once we prove it for rational numbers, it's pretty easy to prove it for irrational numbers. Note that the integers and the natural numbers are not dense in R. For an example, I'm going to give the interval 1/2 to 3/4. Those are two real numbers, so that's a valid interval. We cannot find an integer or a natural number in between them. So we cannot say that the integers and natural numbers are dense. They are not dense. And we're going to prove that the rational numbers are dense in the real numbers. So essentially, by the definition of density, we're going to prove that for every two real numbers, A and B, with A is less than B, there exists a rational number R satisfying A is less than R, which is less than B. So I started off by pretty much reminding everybody that a rational number R is of the form m over n, where m is an integer and n is a natural number. So in order to prove this, we need to find an m over n such that A is less than m over n, it's less than B, then we'll show that the rational numbers are dense. So I'm going to note that B minus A is greater than 0 because we have B is greater than A. And so the amazing Archimedean property tells us that we can find an n in n such that 1 over n is less than B minus A, or equivalently that A is less than B minus 1 over n. And essentially what we're doing this for is we're trying to find an n such that if we have an A here and a B here, and a B here, and we have some sequence of, I'll just call them k's over n's over here, where k is just a natural number. Then if we add another, or we're guaranteed to have a number of this form in between A and B. We can't overstep and completely miss it. We just said that B minus 1 over n is less than A, so we are going to have a form 1 over n is less than, or 1 over n is in between the two. And now we're going to consider an m such that m is the smallest integer greater than na. So in other words, we consider an m such that m minus 1 is less than na minus, or less than m. So essentially we're clumping n with a here because we already found n. We already found an n by the Archimedean property. So we want to just focus on m right now. And so we're going to kind of clump n with a for now. So if we kind of just ignore this left part and focus on this right part, we can see that a is less than m over n. And that's another reason we wanted to clump n with a, so we could get this m over n that we wanted to see. So now we have that a is less than m over n. If we focus on this left inequality, we find that m is less than na plus 1. And I should mention, the reason we chose m-1 and m is because it goes back to the idea that we did up here, that we chose our n such that we can't take a step and step over the entire interval. We're going to have to find a number in between them. So by choosing m so that it's greater than n, we pretty much did that. We just said that we're choosing something so that we're going to have something in between a and b. So back to the proof, we have that m is less than na plus 1. We recall that a is less than b minus 1 over n. And that was from this part when we defined our n. So knowing that a is less than b minus 1 over n, we're going to argue that m is less than na plus 1. So that just comes from this left inequality. We're just adding 1 to both sides. M is lesser than na plus 1. And we know that a is less than b minus 1 over n. So we're just going to say that's less than, and then we're going to replace a with b minus 1 over n plus 1. Now distributing, that gets us nb minus 1 plus 1 equals nb. Putting everything together, we get that an is less than m, which is less than nb. Dividing everything by n, which remember we defined as not equaling 0 because it's a natural number. We have a is less than m over n less than b. So because we used arbitrary numbers, the rationals are dense in the real numbers. And I just realized that I never defined the natural numbers. And that is a problem because there are multiple definitions of the natural numbers. Essentially, I'm not going to do any sort of rigorous proof, but I'm going to call the natural numbers the numbers 1, 2, 3, and it goes on forever. Some people will argue that 0 should be a natural number as well. In this case, I'm just taking the natural numbers to not be 0. Okay, so now we're going to do a little application of density and the Archimedean property, and we're now going to prove that square roots actually do exist. So we're going to prove there exists a real number alpha element of R such that alpha squared equals x for any x greater than 0. You can also prove this for x greater than or equal to 0. I didn't do that because it's very easy to prove it's true for x equals 0. Just say that 0 squared equals 0. Therefore, there is a number that squared equals 0. So to prove it for everything x is greater than 0, for any x greater than 0, we're going to consider the set, which we're going to call T, and that consists of all little t's in R, such that t squared is less than or equal to x. So now, pretty much what I want to do is I want to prove that the supremum of this number exists, or the set exists. We do have to break it up into a few cases, because if 0 is less than x, which is less than 1, we're going to have some different properties than if x is greater than or equal to 1. So if we have 0 is less than x, which is less than 1, then we have 1 over x will be an upper bound of t. And that is because if you think about, just for an example, 1 over 1/2, that's just going to equal 2. So pretty much when we're dividing by these small numbers, we're going to get a number bigger than 1. And therefore, it's going to be an upper bound, because obviously if you square a number bigger than 1, it's not going to be less than or equal to that number, to that number that's less than 1. And then if we have 0 is less than x is less than 1, then x is also going to be an element of t. Because notice if we put x squared, we know that that's... Hold on, let me get some water real fast, sorry. Okay, I am back. I apologize about that. Anyways, We know x is going to be in t because if we take x and square it and it's less than 1, we know we're going to get a smaller number than the unsquared version. Now I'm saying for x is greater than or equal to 1, I'm going to say that this massive number is an upper bound of t. And this may seem like a very strange choice of an upper bound, but essentially all I wanted to demonstrate with that is that when we are using the axiom of completeness, we do not need to find the least upper bound. We just need to find any upper bound, and that will guarantee that the supremum exists. Because remember, the axiom of completeness doesn't say anything about what the supremum is, just that it exists. So we can find this very large upper bound, and that works for the axiom of completeness. We've now proven that the supremum exists. Of course, we do have to prove that it's non-empty, so I just said 1/2 is an element of t. Pretty easy to see. 1/2 squared is going to be 1/4, and that's less than or equal to x for all x greater than or equal to 1. So in both cases, we have an upper bound, and we have that it's not empty. So we know that the supremum is going to exist by the axiom of completeness. And so I'm also going to note, this will be important a little bit later, by the above reasoning, we have that alpha is greater than 0. Where alpha is the supremum of t, that's because we said x is an element of t. For the case where 0 is less than x, which is less than 1, which means we have a positive number in t, which means that its supremum is also going to be positive. And then for the case where x is greater than or equal to 1, we have 1/2 is an element of t. Again, we have a positive number in t, so the supremum is also going to be positive. And now we're going to go back to contradiction again, and we're going to assume for contradiction that there is no number such that alpha squared equals x. And we're going to do this by considering two cases. We're going to show that if we assume alpha squared is less than x, we're going to reach a contradiction. And if we assume that alpha squared is greater than x, we're also going to reach another contradiction. Remember that alpha is the supremum of t. So, case 1, we are going to consider when alpha squared is less than x. So we're assuming that for the set t, the supremum, if we square it, it's still going to be less. It's going to be less than x. So essentially what we want to do is we're going to construct a number slightly bigger than alpha, where this element equals alpha plus 1 over n. N is a natural number. So we're going to square this number. Pretty much we're just substituting alpha plus 1 over n in here and there. And when we square it, we get this result. And we know that n squared is greater than n. And so what we can do is we can take this and just replace the 1 over n squared with a 1 over n. And that keeps this inequality as less than, because notice that if we flip this inequality, we get 1 over n squared is less than n. So that's where this less than comes from. And so essentially we did that just to get rid of the n squared term. That's valid because we're not saying this equals this. We're get an inequality that we'll use later. So this is much simpler to work with. We can represent it as this. And then by the Archimedean property, we know there's an m in n such that 1 over m is less than this whole number. And you may be wondering how I got that number. And essentially it was just kind of working backwards. I wanted to show that I guess you'll see later on when I do it, but I just worked backwards. And Okay, I'll explain that after I get to it. But essentially, when we take this number, we can rearrange this by multiplying 2 alpha plus 1 on both sides. And we'll get 2 alpha plus 1 over m is less than x minus alpha squared. So we're going to take this alpha plus 1 over m squared. It's just what we did up here, except we're using m because we only verified that it's true for n and above. So then we have alpha plus 1 over m squared is less than this. That's what we concluded up here. And that's going to be less than alpha squared plus x minus alpha squared. That comes from here. We said that this is less than this. And so when we simplify this right-hand side, we get x. So this is why we chose this kind of bizarre seeming number over here, because I wanted to get to this x eventually. So I kind of worked backwards and figured that if I could somehow get from this point where we got to, if I could somehow introduce a factor of negative alpha squared just to get rid, that should be alpha, not a, but just to get rid of this alpha and leave us with an x, that would be ideal. So I kind of took this, set it greater than this, and then just solved until I got m. That's essentially all I did. So once we plug that in, we get that alpha plus 1 over m squared is strictly less than x. So this demonstrates that alpha plus 1 over m is an element of t. And then that, because a plus alpha plus 1 over m is greater than alpha, we now have a contradiction because we said alpha was the upper bound of t. So we can conclude that our initial assumption that alpha squared is less than x is false. So we know alpha squared is not less than x. Now, if we consider the other case where alpha squared is greater than x, we're going to kind of do the opposite. We're going to construct a number smaller than alpha. So we're going to do alpha minus 1 over n this time, where n is an element of the natural numbers. So when we square this number, we again get the same thing, just with a minus instead of a plus. And then this time to eliminate the 1 over n squared, I just decided to get rid of it and keep this greater than sign. So again, we're not saying that these two are equivalent. We're just saying this one's greater than the other, and then we'll be able to use that later. So again, we have the Archimedean property. And so we know there exists an L and n such that 1 over L is less than alpha squared minus x over 2 alpha. And again, that came from working backwards from what I know we wanted, and I'll get to that once we go over that. But after rearranging, we get that 2 alpha over L. Again, we just multiplied both sides by 2 alpha, and that's less than alpha squared minus x. And again, I'm going to point out that I know a few slides ago I mentioned that alpha is greater than 0. This is why it's important, because we have a 2 alpha in the denominator. If it equals 0, then we've got a problem, and we would have to consider a separate case. And we know because it's greater than 0, we don't have to do any inequality flipping at any point. So when we take our alpha minus 1 over L and we square it, we get that it's greater than this. Again, this holds because we have this is equivalent to this, which is greater than this. So we're using the inequality there. And then we found that 2 alpha over L is less than alpha squared minus x. Again, so what I did here is I worked backwards. I knew that I wanted to get rid of this alpha squared and leave us with x, so I set this expression or less than this, and then just solved for L. And so what we just did is we proved that alpha minus 1 over L squared is greater than x. So we just found that alpha minus 1 over L is an upper bound of t. but that is less than alpha. And we assume that alpha is the least upper bound of t, so we've got a contradiction. So we have to say that alpha squared cannot be greater than x. So essentially, to recap what we did, is we demonstrated that that the supremum of t, which is alpha, we demonstrated that it exists, and it cannot be greater than x, or it cannot be less than x, and it cannot be less than x. So what's left for alpha is that alpha squared has to equal x. And so what's great about that is now we know square roots exist, which is nice to be able to use. Let me check the time really fast. Okay, we're doing okay. So that was kind of chapter 1 of Abbott. That was just like some of the basic theorems and properties that we're going to be using in various places throughout our coverage of this topic. Now we're going to slightly shift gears, and we're going to talk about limits of sequences. So I know...
Before you move on, I did see a couple hands pop up in the audience, so I wanted just to give a little bit of space just in case. You can use the chat over on the side to ask any questions. So I'm just trying to kind of answer those questions along the way for anybody that has them. But now's a good time, kind of before we move into the next topic, if you have any questions, just to toss them into the chat for us to answer.
I'll try to look. For some reason, it's not showing me new chats, so I'm going to try to reopen the chat.
I also kind of secretly wanted to give you a chance to have a sip of water if you needed to as well. It's a lot to do these presentations, right? So
Yes. Yes. Okay.
All right, so not seeing anything specific popping up into chat. I will let you take the floor again.
Okay, cool. And thank you for helping out the questions in the chat. I have like 3 devices open right now, so it's kind of a struggle to pay attention.
Yeah, no worries.
Yes. Cool. Okay, so now we're going to address the limits of sequences. And I know that I said this is Abbott sections 2.1 to 2.2, and that's kind of a lie because I did not include anything about 2.1, but I'm still going to put it there because I think it's an interesting section for you to read by yourselves. It talks about some concepts like what does it mean to add infinitely? Like, is addition the same under that condition? What happens if we arrange terms of sequences? You can find that sometimes you'll get like different results based on how you do that, and it kind of just is a discussion about some interesting cases and why we need to be very precise when we are talking about analysis and how we're proving things. So I'd highly recommend giving that a read, but I wanted to focus on actual content, so I omitted those discussions. So I just wanted to do a brief recap of what sequences are, and essentially it's very simple. It's just a sequence is a function whose domain is the natural numbers. So if you plug in n equals 1, you'll get an output. If you plug in n equals 2, you'll get another output, etc. And that goes on forever. I did put this as a side note. According to Abbott, sequences must be infinite. They must have no end. I know that in some of my math classes, we've defined some sequences as finite. I guess it just depends on the context. For these purposes, we're going to say sequences are always infinite. And there are a bunch of notations for sequences. The first one you can kind of see just by listing out some of the terms of the sequence, and the ... indicates that it's going to go on forever. And then if we have also this one where this kind of describes the rule that we're using. Then we're just saying it goes from n equals 1 to infinity, and then we can rewrite it as we did in the first example. It goes on forever. We can kind of verbally explain what's going on. We have the set a sub n, And then where each a sub n is equal to 2 to the n for each n in the natural numbers. And then, so that's more of a closed form. We have a formula for each a sub n. We can also define it recursively, which pretty much means we have an x sub n. We give what that first term is, and then we define the remainder of the terms based on that initial term. So we get more definitions, yay. And we're gonna be talking about epsilon again. So a sequence a sub n converges to a real number a if for every positive number epsilon there exists an n in n such that whenever n is greater than or equal to n, it follows that the magnitude of a sub n minus a is less than epsilon. So that's a lot of conditions and stuff. Essentially, if we I'm just going to draw a basic graph. Essentially, if we have I'm going to call this our a, that's going to be the limit that it converges to. It's saying that we can have sequences that do all this stuff at the beginning, whatever, but eventually, if it converges, we can find an n such that for all terms greater than that, it's going to fall into this kind of window. All terms are going to fall into this kind of window where you have a minus epsilon and a plus epsilon. And then you can, if it converges, you could then find another n, I'll say n sub 1 later on, and maybe you can take that epsilon to be a smaller number. So essentially it's just saying that for any epsilon, no matter how small you make it, so you can make it so it's almost like this window is 0, it's so small, you can always find a natural number such that all terms greater than that are gonna be in that window. And that's kind of what I said here, or what Abbott said. But if we have a real number a and r and a positive number epsilon greater than 0, they denote the set v sub epsilon of a equals the set x and r such that the absolute value of x minus a is less than epsilon. So again, that would be like this neighborhood, the epsilon neighborhood of a. And then these are just a few common notations of what a sequence converging might look like. This one's pretty basic. It's just saying that we have a sub n and it's going to a. This one always looks weird to me because I'm so used to having like n goes to whatever down here from calculus, but the assumption is that we have an infinite sequence. So that's all that the limit could be referring to. There's no need to put anything down there. But then again, this notation is very similar. It just includes that n goes to infinity. Now, there is a topological definition. I once asked my professor what topology is, and I tried to pay attention, but then she started talking about how coffee cups can equal donuts, and that kind of distracted me. So unfortunately, I cannot give you a clear definition of topology, but I know that there's going to be topological discussions later on in these meetings. So a sequence, according to the topological definition, we have a sequence converges to A if given any epsilon neighborhood of A, there exists a point in the sequence after which all of the terms are in the epsilon neighborhood. In other words, every epsilon neighborhood contains all but a finite number of the terms of a sub n. That should not be a surprise. That's literally what we said up here. We just said that if there's an epsilon neighborhood, eventually we can find an n such that all terms greater than that are in the epsilon neighborhood. And we're keeping going. More theorems and definitions, yay. This one's a little out of place, but I'm going to be using it shortly, so I thought I'd introduce it. We have the triangle inequality that pretty much says that absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. This is a very important inequality that will be used very, very, very often. so it's worth getting used to. But so I decided to put a little bit of a motivation behind it. This is not a proof, just a slightly less formal way of arguing it. So if we have both of them are greater than 0 or both of them are less than 0, that's equivalent to just taking the magnitudes of each and summing them together. For example, if you have 5 plus 7, that equals magnitude of 12. That's really no different than doing magnitude of 5 plus magnitude of 7. It works. If one is positive and one is negative, then we have to be a little bit more careful. So we're gonna take without loss of generality, and that term essentially means that we're just going to pick one to be negative and not the other, and we can say without loss of generality to imply that we could have taken the other one. It doesn't really matter if we could go ahead and prove both, but it's pointless because we only need to show it for one. So we're gonna take b to be negative. And so we're going to say that a plus b, the magnitude, is equal to a minus the magnitude of b. So again, if we said like a equals 5 and b equals negative 3, right? That all that's saying is that we can take 5 minus 3. That's all we're doing. And we know that's going to be less than or equal to a plus the magnitude of b. And because now these are both positive numbers, we can just reintroduce the absolute value signs of a, and we get magnitude of a plus magnitude of b. And so we just showed that magnitude of a plus b is less than or equal to magnitude of a plus magnitude of b. It's just the general idea behind that statement. And then another definition, we're not going to do much with divergence right now, but a sequence that does not converge is said to diverge. So if you consider a sub n equals n, pretty much that's going to diverge because it's just constantly getting bigger. It's going to literally be like the terms of the sequence are going to be 1, 2, 3, 4, 5, right? As you can probably see, this is going to go off to infinity, so we're not really going to have a nice convergence. Another frequently used example of divergence is negative 1 to the n, because notice if you have a real number line, you're just going to bounce back between 1 and negative 1 the whole time. So as soon as we choose like an epsilon that's like 1/2, even if we find that one point fits in there, the next point's not going to fit in there. And so that also diverges. And then I also wanted to introduce the idea that the limit of a sequence, when it exists, it must be unique. And we are going to actually prove that. So essentially, a big part of limit proofs is doing scratch work. So I included a slide just to do some scratch work. And so we kind of want to work backwards from where we want to get to. We want to kind of get that if, I'm going to say if a sub n minus a, say like it converges to a is less than epsilon, and we know that b sub n is less than, or no, we want a sub n still, a sub n minus b less than epsilon. So we're trying to just generally show that if it converges to two limits, a and b, then we have these limits must be the same. And a more rigorous definition of these two numbers being the same is if we have absolute value of b minus a is less than epsilon. For all choices of epsilon, then the numbers are equivalent. So that's where we want to kind of go backward based off of. We want to kind of get here eventually. So when I see something like b minus a, I immediately think of somehow can we add these two intervals together? And so in my mind, I think, okay, how can we get b minus a when b is negative and a is negative? So I'm just going to use the property of absolute values to rewrite a sub n minus b as b minus a sub n. And that works because a sub n minus b equals negative a sub n minus b. And then if you take the magnitudes, right, that negative just becomes a positive. And so, I literally just wrote the same thing. That should be b minus a sub n. So those two are equivalent with absolute values. So now we have b minus a sub n. We have a sub n minus a. I'm playing around a little bit. This is not formal by any means, so I may do stuff that's technically incorrect, but then we'll come back and fix all of it when we go to actually prove it. So I kind of want to see what happens when we add the insides of these absolute values. So we'd have a sub n minus a, and then we'd be adding b and subtracting a sub n. And when we do that, these go away, so we get absolute value of b minus a, which is great, that's what we wanted. So then I'm looking back at, okay, what did we actually do? And we just added these two together inside, and we're going to use the triangle inequality here. We know that this, because we added the insides, are less than equal to the sums of the individuals. That's just triangle inequality. And okay, I'm going to move this down. And because we know that a sub n minus a is less than epsilon, and b minus a sub n, magnitude of that, is also less than epsilon, we are going to find that this whole thing's less than 2 epsilon. Now, I don't love the 2 epsilon because that is not exactly what the theorem states. So what I'm going to do to fix this is I'm just going to call this epsilon over 2, and I'm just going to call this epsilon over 2. And that might be a bit confusing at first because it's like, why can't we just divide it by 2? But the general idea is that the Archimedean property says that, not even the Archimedean property, but the definition of a limit just says that it converges, that we take any real number we want that's greater than 0, and we can find a natural number n so that every term after that is less than that. So it doesn't matter if we choose epsilon over 2, it doesn't matter if we choose square root of epsilon, like we can kind of choose whatever we want, and that will still hold as long as we choose something that's greater than 0. So essentially by defining the epsilon over 2, that's going to change this to over 2, this is going to change this to over 2, and we're just going to be left with epsilon, which is exactly what we want. So like I said, this is just scratch work, not technically correct. Do not take anything I just did as a proof or super correct or anything. That's just kind of the motivation. Now when we actually go to write it up, this is when we want to kind of take things more seriously and be very accurate. So I'm going to start off by saying let epsilon be greater than 0 be an arbitrary real number. That's important because that's part of the definition of a limit, is that epsilon has to be greater than 0, and we can do it for any epsilon greater than 0. So then I'm just going to let the limit of a sub n equals a, and it's also going to equal b. So again, we're showing that if there are two limits, they're both the same number. So we know, based on the definition of a limit, that there exists an n1 in the natural numbers, such that whenever n is greater than or equal to n1, absolute value of alpha or an minus a is less than epsilon over 2. Again, the epsilon over 2 came from the scratch work we did. And then there also exists in n2 in n, such that whenever n is greater than or equal to n2, magnitude of a n minus b is less than epsilon over 2. Again, that came from scratch work. And essentially, I just used two different n values to indicate that it might be different for each one. It might not happen at the same n value. And then I kind of specified what we talked about in the scratch work. By the properties of absolute values, we can just kind of rearrange the terms inside, and that's less than epsilon over 2. So now I'm going to define a third n, n3, and I'm choosing that to be the maximum of n1 and n2. And that is simply because if we have n1 and we have n2, right? If we have that for n2, we have for a sub n minus b. So if we have for after n2, we're very close to b. Notice that n2 is after n1, so it's going to hold for after n1 too. But if we tried to pick something here, then this first sequence, yes, it would fit the definition of a limit, but this second one, but it's not less than n2, so that's problematic. So by choosing n3 to be the maximum of them, we assume that this kind of definition of convergence applies to both of them. So we're just choosing n sub 3. And for n's greater than that, we have the triangle inequality, which implies, and this is kind of just going backwards from what we did in the scratch work. We have b minus a equals a sub n minus a plus b minus a sub n. And that you can separate by the triangle property, or triangle inequality, and we get back to epsilon. So we have that b minus a is strictly less than epsilon. And this is true for any epsilon greater than 0. So by definition, a equals b. So we've just proven that if the limit of a sequence exists, it must be unique. Cool. Now I kind of wanted to give a little bit of an outline of what exactly a limit proof entails. So we saw a little bit of it in this last proof. For scratch work, we want to find an n that depends on epsilon. That's pretty much our entire goal of scratch work, is just to find the n. And the scratch work isn't included as part of the proof. If you're writing this out for school or something, you should definitely indicate that your scratch work is not part of your proof and it's separate. But some professors might give partial credit if you messed up during the scratch work, but they consider you did some stuff correctly. So I like to include it. I just make it very clear that it's not part of the actual proof. So then we are going to write our proof, and they pretty much all start off with let epsilon be greater than 0, be an arbitrary real number. And then next you define your choice of n from the scratch work. I also made a little note, how do we know that we can always find an n greater than or equal to this number? And it goes back to the Archimedean property. So even though we're not necessarily citing the Archimedean property every time, this is where it comes from. And then our third and final step is that given our choice of n, we can find that for all natural numbers greater than or equal to that, we have this inequality, which was part of the definition of limit convergence. So I wanted to give a few more examples of limit proofs. This one's a little simpler. So we're going to start with this. Essentially, remember, we want that n plus 1 over n minus 1, because that's the limit. We want that to be less than epsilon. So if we do some simplifying in here, we get n over n plus 1 over n minus 1 less than epsilon. This is what we want, of course. This just equals 1, so those go away, and we're left with 1 over n is less than epsilon. And I just got rid of the absolute values because n is a natural number, so 1 over n is going to be positive. And then we want our n to depend on epsilon, so I'm just going to flip this and say n greater than 1 over epsilon. And so our choice will be n such that 1 over epsilon is less than n. And once we have that, we can go to writing our proof. So again, it starts off with let epsilon greater than 0 be an arbitrary real number. And then from our scratch work, we chose our n in the natural number such that n is greater than 1 over epsilon. So then for any n greater than or equal to our big N, we can write that this inequality, n is greater than or equal to n, which is greater than 1 over epsilon. And cutting out the middleman, we just have n is greater than 1 over epsilon. Rearranging the inequality, again, we're just going backwards from what we did in scratch work. We get that 1 over n is less than epsilon. I just reintroduce the absolute values. I'm kind of building back up to what we want to end up with. So I then specified this little scratch work that we did. We found that 1 plus n over n minus 1 equals 1 over n. I just expanded this to this, and that is what we wanted. So we just proved that the limit is 1. So for example 2, this one's a little more complex because notice we have a cosine of n in the numerator. So essentially, for the scratch work, remember that we want 2 cosine n over square root of n, and we want that to be less than some epsilon. So what I'm going to do is I'm going to notice that 2 and square root of n are already positive, so we have 2, and then we just have to keep the absolute values around cosine because that's what can fluctuate. And that's going to be less than epsilon. I'm going to go ahead and flip the inequality, get the square root of n out the top, and that's going to lead us to square root of n over 2 cosine n, and that's going to be greater than 1 over epsilon now. Now, what's causing a little bit of a problem is that this 2 cosine of n is not very clear. It fluctuates so much. So what we're going to want to do, this is horrible, I'm going back to the top, is we're going to try to find a number so that we can fit a number in between here, or we can keep this inequality correct and still have it be greater than 1 over epsilon. So the way I'm going to think about this is we have a cosine n in the denominator. Because we have the absolute value, we have the maximum value of cosine n equals 1. So for our biggest value of 2 absolute value of cosine over n, our maximum value for that is going to be 2. Now note that if we have this guy being its maximum, that means that, okay, I'm going to write it as square root of n over 2. Essentially, I'm just replacing the absolute value of cosine of n with its maximum value. So square root of n over 2. And because that's less than the denominator is greater, we are going to have that this is going to be less than square root of n over 2 cosine. Let me make sure I got this right real fast. Yes. Wait, yes? Okay, yeah. And then we're going to squeeze that over 1 over epsilon. Should I do it right? Sorry, I'm second guessing myself right now.
No, you have it right because you want to squeeze that root n over 2 in between, right? So you can get the inequalities the way that you want. Yes, you're good.
Cool, thanks. Great. So we have that. And so I'm just going to focus on this part right now. I'm going to have the square root of n over 2 greater than 1 over epsilon. Multiply both sides by 2, which leaves us with root n is greater than 2 over epsilon. Square both sides, and n is greater than 4 over epsilon squared. And I apologize for my horrible all over the place scratch work. My scratch work is always very messy, so I apologize. But this is kind of what we're going to go for right here. Now we can move on to our proof. And we're going to let epsilon be greater than 0, and we're going to let it be an arbitrary real number as normal. And we're going to choose our n so that n is greater than 4 over epsilon squared, which is exactly what we wanted, or what we found in the scratch work. So then for any n greater than or equal to n, we see that n is going to be greater than or equal to big N, which is greater than 4 over epsilon squared. Again, we cut out the middleman, and we're left with n is greater than 4 over epsilon squared. Now rearranging the inequality, going backwards from what we did in scratch work, we're going to get square root of n over 2 is greater than 1 over epsilon. And then again, we're using this fact that 2 absolute value of cosine n is less than or equal to 2. And we're just going backwards. This is exactly what we found in scratch work. And I cut out the middleman yet again, which got us here. And then I just rearranged it. I literally just worked backwards and reintroduce the absolute values, flip the inequality, and we get back to what we wanted to get. We got that the sequence minus the limit is less than epsilon. So that's a general proof, and yes, it can be a little bit confusing at times. Not all sequences are very nice, so you kind of have to play around with how can we squeeze what inequalities where. How can we maximize the denominator, minimize the denominator to get an inequality that works for us to get our end result? So the scratch work can sometimes be a little complex, and you kind of have to be a little bit creative sometimes. But it works out if you can find a good solution. So moving on, I'm going to talk a little bit about properties of limits. And for those of you who have taken calculus, you'll probably be very excited because we are going to go over some of these properties that allow us to kind of skip over using the formal proof of some of these limits. So I said even more theorems and definitions because I already had a slide called theorems and definitions, and then I had another slide called more theorems and definitions. So I thought it would be appropriate to have even more of them. And a sequence x sub n is bounded if there exists a number m greater than 0 such that absolute value of x sub n is less than m for all n and n. And that's just essentially saying we have a negative m less than x sub n less than m. So we can squeeze kind of all of our terms in between these two numbers. And that definition leads us into the theorem 2.3.2. Every convergent sequence is bounded. So we're going to prove that really fast. And
problem solved.
So to do that, we're going to assume that a sequence converges to A. That means for every positive number epsilon, there exists an n and n that for n greater than n, negative epsilon plus A is less than A sub n, which is less than epsilon plus A. So I'm going a little fast. We're getting short on time, so I'm going to go a little faster with this. But essentially what this is saying is if this is our limit A, we have some number n, again, which by definition, if these are epsilons plus A, etc., and there's just some number where we can squeeze all the remaining terms in there. But we also have terms before that n, right? And those may not necessarily fit inside that epsilon neighborhood. So essentially the way we're going to take care of this is we're going to kind of set an epsilon right now. We're going to just say for now epsilon equals 1. And so I'm going to just rewrite this inequality using 1. And we're going to have this inequality. So we have to account for the fact that a could be negative. So I'm just going to write that the magnitude of a sub n is less than absolute value of a plus 1. And you can verify for yourself that that will be true. And this is for all n greater than or equal to that big N. So that we're talking about this section over here. Now, there are n minus 1 terms before a sub n. So now we got to consider all of these terms. We know there's a finite number of them because you're going to talk more about like cardinality and countability later on. But essentially we can count the number of elements before n. And so we know there are n minus 1 terms before a sub n. This is a finite number. And so we can find a maximum of that value, of all those values. We also do note that there may be a case that since we chose epsilon to be 1, there could be a case in which all of our numbers naturally fall in, all of our terms naturally fall into that epsilon neighborhood. So considering all of that, we're just going to take m to be the maximum of all the individual points over here and our epsilon value, or epsilon neighborhood value, which we determined was the absolute value of a plus 1. So we know the maximum exists, just we take whichever one is the biggest, and we say that that's greater than magnitude of a sub n for all in n, and we've just proved that any convergent sequence is bounded. Okay, now here are the limit properties that are amazing. So if we have limit of a sub n equals a and limit of b sub n equals b, if you multiply something inside of the limit, you just multiply that constant times that limit. In addition, if you add two sequences, you just add their limits. If you multiply two sequences, you multiply their limits. And then if you divide two sequences, you divide their limits as long as b does not equal 0. If it does, then you have a problem. This is called the algebraic limit theorem. I'm going to briefly do a proof for each of these with special conditions for some of them. For example, for 1, I'm going to prove 1 when c does not equal 0. It's pretty easy to prove for when c equals 0. So I'm just going to focus when c does not equal 0. And so this one's the one where if you multiply a constant by a sequence, you're going to just multiply the constant by the limit. So scratch work. Again, we like that for limits. We want to eventually get to c a sub n minus c sub n, or c times a is less than epsilon. We can pull an absolute value of c out of there and get a sub n minus a left over is less than epsilon. So if we choose a sub n minus a is less than epsilon over c, absolute value of c, we'll be good. And by the Archimedean property, we know there's an n in n, such that for all n greater than or equal to that, this will be true. So we're just going to use that. We're going to let epsilon be an arbitrary positive real number. Again, we know there exists an n and n, such that what we just proved in the scratch work holds. And again, we're just going backwards. Bring that absolute value of c right in front. Simplify the left side, and that tells us that we have that, which is exactly what we wanted, so we just proved the limit. And again, I know I'm going a bit too fast through these, so I'll definitely make these available so that you guys can come back and look at them. And then proof of 2, and for refresher, 2 was the one where you add their limits, then if you add the sequences, then you add the limits. And for the sake of time, I'm actually going to skip the scratch work for this because this is almost identical to a proof we did earlier. It's almost identical to the proof where we use the triangle inequality and prove that limits are unique. So essentially, what we do for this one, we just find an n1, so that the sequence A sub n converges, and n2 so that the sequence B sub n converges. Pick the maximum, use the triangle inequality, add the two together, and you'll get that it's less than epsilon, which is what we wanted. So yeah, I know we went through that very fast, but that's literally like the only difference between this and the other proof we did, is that we just switched these terms around in the other proof and then got something slightly different, but it's the same idea. Proof of 3, if A does not equal 0. So limit, if you multiply the sequences, you'll get the product of their limits. So this one, essentially, we want to find that an b sub n minus ab is less than epsilon. So this one's going to be a little more complicated than the previous few, but essentially, I believe, what did they say they add? Oh, that's proof of, oh, that's proof of 2. Let me go to proof of 3. That's actually the one we're working on. And then they just added, they subtracted, so they did a sub n, b sub n, I believe it was a sub n b. I want to make sure it should work either way, but a b sub n. But I want it to be consistent for when we actually do the proof. A b sub n. And then they added a b sub n, and that's okay. We just added 0 essentially, just in different ways. Minus a b, and we want that to be less than epsilon. So now we're going to use the triangle inequality again. We're going to say that this is less than or equal to a sub n b of n minus a b of n. And then that this part is less than a b sub n minus a b. We want that to be less than epsilon, of course. So now we're just going to pull out a common factor. Over here we have b sub n, so we're going to do b sub n times a sub n minus a, and this is going to be this is going to be a absolute value of a b sub n minus b, less than epsilon. So we're going to use by now our common trick of letting each of these be epsilon over 2. And so for this right one, if we want absolute value of a times absolute value of b sub n minus b less than epsilon over 2. This is pretty simple. We just divide by absolute value of a. Again, this is because we defined a to be not equal to 0. It's not too difficult to prove that if a does equal 0, then it still holds, but for now we're just not going to do that. So if we have, absolute value of b sub n minus b, that's going to be less than epsilon over 2 times magnitude of a. Now it's a little bit harder for this other sequence because we have absolute value of b sub n, a sub n minus a, and we want that to be less than epsilon over 2. It's really hard because dividing by a sequence doesn't really help us much. That tells us kind of nothing. Okay, now it's telling me that I'm slouching too much. Come on, okay. And then we have, so what we're going to do for this is we're going to use the idea that b sub n is bounded. And so we're going to find an m such that b sub n, absolute value of that, is less than or equal to m. And we know it's bounded because it's a convergent sequence, and we prove that all convergent sequences are bounded. So we're going to say that absolute value of b sub n times absolute value of a sub n minus a is less than, I'll do it down here, is less than or equal to m times a sub n minus a is less than epsilon over 2, then you can just divide both sides by m. And that's less than epsilon over 2m. Again, we're assuming that m does not equal 0. If it does, you'll have to work around it a little bit. But, yeah. So we get that inequality. And so we are just going to choose our n1s, we'll put like n1 here, n2 here. So we're just going to choose them appropriately so that these are guaranteed by the Archimedean property and the definition of convergence. So now to actually write the proof, we're going to let epsilon be a positive arbitrary real number. You should be getting tired of that line by now. But you'll use it a lot. So we know that since b sub n is convergent, there exists an m greater than 0 such that b sub n absolute value is less than or equal to m for all n in n. And again, that's because that's what we talked about. Come on. That's what we talked about in the scratch work. And then we are then going to take our n1s, our n's as determined. We have our n1 in n such that this inequality holds, which is what we found in our scratch work. We're going to take n2 in n so that this inequality holds from our scratch work. Again, we're going to take n3 to be the maximum of those two. Take a natural number, all natural numbers bigger than that. And we just unmultiplied kind of. So we, or undivided, we multiplied by m on both sides, and then we multiplied by absolute value of a on both sides. And that got us back to where we wanted. And so then once you put all the pieces back together, you have this, which is what we wanted to prove is less than epsilon. We broke it up using the triangle inequality. We pulled our factors out, and we find that it's less than epsilon. So we just proved that guy. Sketch proof, what time is it? Okay, I'm going to skip the scratch work for this and kind of just go over it because this one, you kind of prove in a slightly different way. Because note, this one's the one that if you have a sub n over b sub n, that goes to a over b. Now, essentially, if you realize that this equals a sub n times 1 over b sub n, then that is also equal to a times 1 over b. So if we can just prove that 1 over b sub n converges to 1 over b, we can then use part 3 that we just proved to get here. So I just did a little bit of a sketch of the proof of 4. Essentially, we're going to be trying to prove the statement that 1 over b sub n minus b is going to be less than epsilon for all epsilon greater than 0 and some n greater than or equal to the n we choose. Or 0. Oh, thank you. Yes, so essentially we're just going to prove this for any epsilon greater than 0 and all our conditions for n's. So just a little sketch is that we know there exists an n1 and n such that for all n greater than or equal to n1, b sub n minus b is less than absolute value of b over 2. Notice that this does not have an epsilon in it. That's okay, we're going to introduce it elsewhere. It still holds because absolute value of b greater than 2 is a positive number. So this does hold by the definition of convergence. And then
What about me? He wrote me
that
into
means
this.
that
That one over there wrote me
b
into
sub
this.
n
He
is
wrote
going to
me
be
into
greater
this.
than this because we're no longer subtracting the b from it. And then we know that there exists an n sub 2 in n such that for all n is greater than or equal to n sub 2, we have that this inequality is less than this nice number. Now, the motivations for these numbers would be a little bit harder to find. You'd have to probably do a lot more scratch work. If we had more time, I'd go over it. But I believe you can read in the book, and they might explain it a little more. But again, we're going to take n greater than or equal to our n sub 3, which is the max of the two numbers. Common strategy like we've seen. And if you work with this side a little bit by multiplying, by trying to get a common factor or common denominator, you result in this guy. And that, using our inequalities, we have this guy corresponds to this guy, and that guy corresponds to this guy, and you notice there's a squared here, not here. That's because we have this extra factor of absolute value of b in the denominator. So that gets us to this, which works out to be epsilon. So we found that it converges. And then again, now that we know that this is true, you can go back and prove that this is true using part 3. And then we have one final theorem. So again, if we have limit of a sub n goes to a and b sub n goes to b, so we have that if all of the terms of a sub n are positive, then the limit's also going to be positive or equal to 0. If we have two sequences, one's less than the other, then the inequality is going to hold for their limits as well. And then number 3 is very similar to number 2. So if we have a constant less than all the terms of a sequence, the constant's going to be less than the limit. And if we have a sequence less than a constant, then we have that limit is going to be less than that constant. This is called the order limit theorem. And just some proofs, motivations. The first one's the proof, the other two are motivations. So remember, for the first one we said if a sub n is greater than or equal to 0, then the limit must be greater than or equal to 0. So for a contradiction, we're going to assume that the limit is less than 0. So we strategically are going to pick an n such that this inequality holds true. Essentially, all that does is if we have an a which is less than 0, we know that we set this up to be this way so that if you do a plus magnitude of a, you're going to get right back to 0. So we've just said that we found that the difference between so we just found that all of our terms are going to be in here for all n greater than or equal to n. And so we've just found that there are a sub n's that are less than 0. And that contradicts the assumption that we had every term greater than 0. So we can state that if a sub n is greater than or equal to 0, then a is greater than or equal to 0. Yeah, so that was just the strategic choice of absolute value of a as our kind of epsilon to prove that there has to be elements less than 0. Now, just for a motivation for 2 was that if a sub n is less than or equal to b sub n, then a is less than or equal to b. So we can use part 1. We know that this converges to this by the theorem we just proved, the algebraic, what was it called? Algebraic limit theorem? Yes. Yeah. And so we also know that because b sub n is greater than a sub n, their difference is going to be greater than 0. So then we can just use this as our kind of like our a sub n as in part 1, and this as kind of our a in part 1. And using part 1 implies that this is going to be greater than 0. And then my amazing motivation for part 3 was just use part 2. It was very similar. We're just dealing with a constant instead of a sequence. So yes, that was, let me see the time. Did I stay under? Okay, 2 minutes under, yay. But that's generally the ideas, like kind of the foundations that you guys are going to be using throughout this discussion of real analysis. Again, I apologize that I kind of had to rush through the end. but I will make sure you guys can see these slides so you can go back. So if you guys have any questions, comments, criticisms, anything along those lines, let me know, and I'll be happy to talk about it.
So thank you so much, and don't feel bad about rushing a little bit at the end. It was actually really nice to see the scratch work for some of those kind of preliminary proofs that you were doing. I think that's really helpful. At least some people in Twitch chat were saying it was helpful to see some of that. So that's
Okay, yay.
much appreciated.
Of course.
Vita, of course, says thank you so much in Discord. ML1
Yes,
is
I'm
saying
just
thank you
opening the
over
chat
on
now.
Twitch. Yeah.
You guys got to see my iPad being mean to me a little bit, calling me out.
Calling you out for slouching. I had that. It gave me a good laugh.
Yeah, it happened multiple times too. I'm like, come on, don't call me out like this. But it's a good reminder.
So yeah, I think what you said here is fantastic. I loved looking at these slides. I thought they were put together really well. For those of you that are kind of taking the reading group, I definitely encourage you to go back through some of the proofs of what we saw today and try to get through that scratch work on your own. Try to see if you can set up what that proof might look like, and you can even post in the forums as well, right? If you're kind of working on some stuff and you want to kind of show us what you've been working on and get some feedback on your proof structures or anything like that, just do that right in the Mandelbrot mathematics server under the real analysis class. We're happy to help you out with that kind of stuff. Thank you again, Dingus, so much for taking your couple hours out of your, well, more than a couple hours out of your week to present on a topic that I think is a really fun introductory topic for real analysis.
Of course, yeah. Thank you for having me.
Yeah, you're more than welcome. I'm going to go ahead. I'm just going to mute myself here in the mathematics server so that I can finish off things over on the Twitch side, and then I'll bounce back in case you want to debrief anything after, okay?
Okay, sounds good.
That's what I want. That's what I want, right like that. Okay, so thanks very much, everyone over on Twitch, for coming and hanging out for a little while. We are going to... Oh, thank you very much for the wishes. Laz... I've been giving away QED points for those that have been wishing me a happy affiliate anniversary. I can't believe it's been like 3 years already. It's crazy. We're going to go ahead and we're going to get a raid started up. I think Phobos is still on, right? Yes, excellent. So Phobos is still going on the mathematics. So we're going to get a raid started to pop up over there. Thanks again. Our next real analysis session is going to happen next weekend. I'll be leading the discussion there. We'll be trying to tidy up some stuff with cardinality, maybe doing a little bit more of these kind of like sequential limit proofs, and seeing a little bit more in-depth kind of how to deal with different styles of proofs like contradiction, contrapositive, and induction, in case those come up in the next couple weeks. So we have our next couple presenters lined up after that. So Slender is going to be coming in to do a little bit of the topology over the real numbers, and then Coffee has been putting together some slides for functional limits, which is kind of like that first place, right, where we get to see that really nice connection back to calculus. So super excited for the next coming week. So get excited. February is going to be a lot of fun with our Intro to Real Analysis course. Until then, I probably won't see you. Well, Talos has his stream tonight, so if you're hanging out over in Talos' stream, I'll probably pop in to say hello. And then we have the linear algebra reading group that Zach and I are doing, like the problem-solving sessions. That's happening tomorrow morning. We changed the time to 8 a.m. Pacific, so I'll post some reminders up today just to let you know some of the things that are happening. But you can always check out the calendar for the most up-to-date stuff. So let's go say hi to Phobos. If you need a raid message, I will type it into the chat, and we'll talk to you guys later. Bye!